To wrap up this chapter, we'll talk about rational inequalities. And thankfully, this is going to be a bit of an easier topic than graphing, because there's a lot less information that we have to work through. So similar to a polynomial inequality, a rational inequality is any inequality that involves a rational function. And the concept is similar to polynomials, where we put the rational function on one side so that it's related to 0 in some way. But the concept, again, is still similar to polynomial inequalities in terms of their sign charts. The only difference is that rational functions may change signs at different places than a polynomial will. A rational function can change sign at an x-intercept, a vertical asymptote, or a removable discontinuity. For polynomials, all we had to do was check the x-intercepts. For a rational function, we check the x-intercepts, as well as the vertical asymptotes and the removable discontinuities, but notice that we don't say anything about horizontal asymptotes. When the question is solely about an inequality, we do not need horizontal asymptotes. Let's look at the graph again. G of x equals 2x squared plus 1 divided by x squared plus 2x minus 15. We saw that it had vertical asymptotes of -5 and +3, and that it had no punctures, or no x-intercepts. So what we're going to do is draw a sign chart only with the vertical asymptotes, basically the only places that our function could change sign. Also similar to when we were graphing a rational function, we needed to pick a test value. So we're going to pick a value to the left of -5. Really, we just need to pick something that's around or in between our vertical asymptotes. We just can't pick -5 and 3 exactly. So we choose -6. We see that we get an output of 8.1, which is positive. So I'm going to put a plus sign to the left of -5 on our sign chart. Since this vertical asymptote has odd multiplicity, we know that because the graph is approaching positive infinity on the left side of this asymptote, it has to approach negative infinity on the right side. So I'm going to draw a negative sign to the right of -5 on our sign chart. And by similar logic, the vertical asymptote 3 has odd multiplicity, so our graph will change from negative to positive at this location, meaning that I'll put a plus sign to the right of 3 on our sign chart. And this means our sign chart is complete and I know exactly where my graph is above or below 0. So just to answer an example question, I can say that g of x is bigger than or equal to 0 on the interval from -infinity to -5, not included, union with 3 to infinity, also not included. Now this seems a little strange because if this was a polynomial question and I saw that weak inequality, I would have square brackets. And yes, I definitely would if those were x-intercepts, but those are vertical asymptotes. Points from my graph is not defined. So even with a weak inequality in this case, I still have to use open brackets. I can't include values that are vertical asymptotes because my function is undefined there. So I can't rightly say that my function is equal to 0 or bigger than 0 at that location. It's just undefined. Next, let's look at the function f of x equals x plus 1 times x minus 2 squared divided by x times x minus 1. And this can be expanded out as x cubed minus 3x squared plus 4 divided by x squared minus x. Now when I look at the degrees of the numerator and denominator, that would tell me I would have an oblique asymptote. But since this is a rational inequality problem, I don't care about oblique asymptotes, nor do I care about horizontal asymptotes, at least in the context of this question. The only things I care about are the vertical asymptotes, the x-intercepts, and any removable discontinuities, should they be there. This polynomial is in reduced form. I don't have any common factors upstairs or downstairs that cancel, so I can look at the denominator and derive vertical asymptotes of 0 and 1, both with multiplicities of 1. The numerator, and I'll look at the factored form for this, gives us x-intercepts of -1 and +2, which have multiplicities of 1 and 2 respectively. And since this rational function is already in reduced form, again, there are no common factors, I don't have any removable discontinuities. So using this information, I can go ahead and populate my sign chart with the values 0, 1, -1, and 2, all of my vertical asymptotes and all of my x-intercepts. And make sure to write these in numerical order. Now, just as a bookkeeping process, there are a couple ways that you can label your number lines so that you know whether or not you're looking at an x-intercept or a vertical asymptotes. One of the things that you can do, like I'm doing now, is to use color. I'm using blue for vertical asymptotes and green for x-intercepts. But if you'd prefer another option, here's another way. I'm going to draw closed circles on the number line for all of my x-intercepts, and for my vertical asymptotes, I'm just going to put little dotted lines. Ultimately, this is just a nice bookkeeping technique so that you know what's what. Alright, so like before, we're going to go ahead and pick some test points. I'm going to pick one point to the left of -1 so that I can go ahead and start my sign chart. And I'm going to pick -2. When I plug -2 into f of x, I get -2.67. So I'm going to put a negative sign on the interval from -infinity to -1. Now, one option that I have is to just put test points everywhere else. I can pick a value between -1 and 0, something between 0 and 1, something between 1 and 2, and so on. And even though that is technically a little bit easier in the sense that I don't have to think about multiplicities, it's more computationally tedious. So I'm going to recommend the better option, what I think is the better option, is just to use what we know about multiplicities. We already have the information about where our graph crosses, bounces off the x-axis, or changes sign. So that's really the thing I want to focus on here. Because -1 is an x-intercept with an odd multiplicity, we know that my graph has to cross the x-axis there. So I'm going to go from being negative to positive, which means I'll put a plus sign between -1 and 0. Now 0 is a vertical asymptote with an odd multiplicity. That means I'll also see a sign change. So between 0 and 1, I'll put a negative sign. Again, 1 is a vertical asymptote that has an odd multiplicity, so I'm going to change signs again and then put a plus between 1 and 2. And then lastly, the x-intercept of +2 has an even multiplicity, meaning that my graph is going to bounce off the x-axis. This means my graph does not change sign when it goes to the right of 2. It was positive to the left of 2, and it'll stay positive to the right of 2. So now that the sign chart is complete, we can solve any one of the 4 inequalities that were presented on the previous slide, f of x being bigger than or equal to 0, or f of x being strictly bigger than 0. And we're going to display all 4 just so we can kind of understand the different changes and nuances that might happen. Because in the last slide, I said you can't include vertical asymptotes, but here we have vertical asymptotes and x-intercepts. So what gets a square bracket and what gets an open bracket? Let's go ahead and look at where f of x is bigger than or equal to 0 and where it's strictly bigger than 0. F of x is bigger than or equal to 0 on the interval from -1 to 0, union with 1 to infinity. If this were a polynomial question and everything was an x-intercept, then I would be including pretty much every numeric point in my interval, except for infinity, of course. But I'm not including 0 or +1. I am including -1 because -1 is an x-intercept, meaning that my graph takes on a value of 0 there. So I would have to include that in the set of all x values such that f of x is bigger than or equal to 0, because that counts. But I don't include 0 and I don't include 1 because those aren't x-intercepts, those are vertical asymptotes, and I never include those in any inequality discussion. A rule to remember is the following. When you have a rational function with a weak inequality, the only values that could possibly get square brackets are x-intercepts. Never vertical asymptotes, and never places where I have removable discontinuities. Those will always be open brackets. Alright, and then we'll conclude by giving us the inequality results for f of x less than or equal to 0, and f of x is strictly less than 0. Just like before, I'm just going to read through my sign chart. Instead, I'm going to look for every place where I have a negative sign. So f of x is less than or equal to 0 on the interval from -infinity to -1 included, union with 0 to 1. Again, same thing. I'm including that -1 because that is included into the discussion of where my function is less than or equal to 0. And -1 is a root, making the function equal to exactly 0. But I still don't include the vertical asymptotes because my function isn't defined there. And then for the weak inequality, I just simply exclude the -1, and then we're done.